Right, some brief notes about some of the questions and ideas in Chapter 19. Chapter 19 follows on nicely from the GCSE physics you did when you looked at the turning effect of a force. You looked at levers, you looked at seesaws. It's exactly the same principle. The turning effect of a force, the moment of a force, is a product of the force and the distance to the pivot. Okay, or technically it's the force multiplied by the perpendicular distance from the line of action of the force to the pivot. But all the forces we look at in year 13 single will be perpendicular to the distance. So in the example on the bottom right, if you've got that force acting at that distance, the turning effect about that bit there will be the force multiplied by the distance. So again, the same definition again. If you've got a force acting at that distance and it's at a right angle, which our questions will be, the moment of the force is force times distance, but you have to give a sense to it. So in this case, it's anti-clockwise. That force there, F, around the pivot P acts in an anti-clockwise direction. So if we look at these examples here, which I think match the ones at the beginning of 19A, if that force of 10 acts at a distance of 5 meters from that pivot P, so force of 10 at a distance 5 from P, then the moment will be 50 Newton meters, and you've got to say clockwise. Now, they do like questions where you have things like rectangular lamina, and lamina is a flat shape with no dimension. So if you've got the force acting up here at that corner, down that edge, and you've got the pivot there, because the line of action is straight down there, and because that distance is still 5, the moment is still 10 times 5 Newton meters clockwise. Okay, in 19A question 3C, or in fact all the ones in question 3, they want you to consider a 4 meter long uniform rod weighing 50 newtons. Uniform, the same density throughout. The center of mass is on any line of symmetry. It's in the middle of the rod. It's bang in the middle of a rectangular plate. What do we mean by center of mass? Center of mass, the point at which the weight can be considered to act through, the point at which we're going to draw the weight. So if you look at question 3CI1, then we've got these two forces acting on this rod as described. Can we find the net moment, the resultant moment? Redraw the diagram with the 10 on it, the 30 Newton force, but then add the weight acting vertically downwards from the middle. The resultant moment about P, the resultant moment M about P is 50 times 1. That's the clockwise force. Take 30 times 3 and take 10 times 1, because those two forces are anti-clockwise forces. That one's going that way, that one's going that way. If you stuck a pin here, it's about P, so they've got clockwise and anti-clockwise. That gives you an answer of minus 50 newtons. Since I said that was clockwise, that's minus 50 Newton meters clockwise, or 50 Newton meters anti-clockwise. Right, this is 19A question 4. A 4 by 6 meter uniform rectangular laminar weighs 150 newtons. The laminar is in a vertical plane, and B part 1, it wants the net moment. So there's one force added to that, but we note it was a uniform rectangular laminar weighing 150 newtons. Redraw the diagram, adding the weight, and you've still got this force acting on it. Now, we want the resultant moment about P. So, add in the lines of action of the two forces. That one acts there, that one acts there, and it's the distances to the lines of action. It's not some sort of crazy diagonal distance. It's not this crazy diagonal distance there. Let's get rid of that. It's these two distances, the perpendicular distances to the line of action, which nicely gives us, well, imagine a pin at P. I think both those forces are acting clockwise around P, giving this answer. And then the final bit of the exercise, and this is a bit that thwarted me. I've just been trying to make videos using my stand, but they're too big to upload if I do them straight from my phone, so I've got to change some about the formatting. Anyway, equilibrium questions. If an object is in equilibrium, the resultant force acting on it is 0. We already know that. That's the basis of a lot of the work we're doing. Okay, anything on the inclined planes, resultant force acting is 0. If now the forces aren't acting all at the same point, if we're not considering particles now, we have this second result. The resultant moment is 0 wherever we take moments about. So we might have questions involving things resting on supports. If something's resting on supports, let's say it's resting on these pivots here, then we're going to include reaction forces on the diagram, a reaction at A and a reaction at B. If it's hanging on strings or wires, we're going to include tensions to the diagram, as well as weight. And remember, if something's uniform, the weight acts through its center. Right, and then crucially on a lot of questions, if an object is on the point of tipping or tilting about a point, then we can remove the reactions and tensions at any other points. Okay. Right, at the moment I've just done one example. It's 19B question 6, but when we're close for the break, I'll see if I can get some more videos. So 19B question 6, if you want to read the question quickly. Right, so the first thing is the diagram. So we've got a rod of 5 meters. If you skim read the question, we're told it's uniform, so I'm going to put the weight bang in the center. I'm going to label my A, I'm going to label my B. I'm going to put C and D in the right places. But if you read to the end of the question, when this weight of E is added to it, when the weight of 15G is added to the rod, it tilts about D. Tilts about D means we can get rid of the forces at C. We can ignore that. If it's tilting about D, we can ignore that. So what have we got? We've got a seesaw. We've effectively got, if it's on the point of tilting, we've got this force balancing this force. Okay. If it's in equilibrium, we have a resultant moment of 0. If it's in equilibrium, we have the anti-clockwise forces balancing the clockwise forces. That's the bit to get your head round, because as soon as we write that, the 6g times a half is 3g, divide by the 15g, x is 0.2. Distance from A to E is 3.2. It's not included in the question. If it had asked us to work out the reaction at D, remember what we said about equilibrium. The resultant force is 0 as well, so the upward force has to balance the downward forces. So there's two entirely different things on this page here. There's taking moments, force times distance, anti-clockwise and clockwise, and there is balancing up with down. Two completely different ideas.